Good day, everybody. Thanks, Brent. Thanks for the introduction. Today, I would like to share with you how to get the best possible value and performance out of your mill liners. So let's immediately look at the overview of the material or the content of this presentation. We will start off by looking at the mill liner performance indicators. We will then look at two case studies. In the first case study, we will look at selecting the correct grinding mechanism for your mill. Case study 2, a short case study, but here we will look at optimizing the liner life, mill effective volume, and mill absorb power. And then we will move over to a design comparison between a radial and a spiral discharge system. And then lastly, what to take away from this. So if we look at mill liner performance indicators, what do we consider during the design? What do we aim for during a set of mill liner when we design mill liners? First of all, your grind efficiency. Guys, a mill is the only machine in the milling circuit responsible to grind the material. So grind efficiency is really a priority. The throughput, this can be significantly influenced by your set of liners. The wear life of the liners, structural integrity. We need to make sure that the liners protect the very expensive mill shell throughout the liner life. Then discharge efficiency, we will spend a lot of time on this, and we see this as an area of development and improvement in the mill liner design. Also, ease of installation. Over the past few years, this was a very big focus point where we've seen robotic mill liner handlers. We have even seen pre-programmed robotic mill liner handlers, and that is all to reduce the installation time and to make it safer. And then lastly, the environmental impact of the liners. Multotec and our customers are very passionate about the environment, and here we aim to reduce the amount of the material, specifically the amount of rubber left towards the end of liner life. So as an introduction to the first case study, I would like to share a few slides with background information. The first one, the type of grinding mechanisms in a mill. Impact grinding, that is when your grinding media falls directly onto your ore particle. This is to break larger, harder material. Abrasion or shear, that is when two ore particles move relative to each other and hence removing material between them. Attrition grinding, very similar to abrasion or shear, but this is when the ore particle is trapped between grinding media and there's relative movement between the two grinding media, or even more than two pieces of grinding media. And then lastly, compression grinding. This is a combination of impact, abrasion, and attrition grinding. Then guys, I also want to have a look at the mill zone definition, the different zones in your mill. On the right-hand side is a SAG mill, 8.5 diameter SAG mill, and on the left-hand side, a 2.5 diameter preferential mill used in the diamond industry. Now, if I plot this preferential mill to the same scale as the SAG mill, this is what it will look like. You can see you can fit multiple preferential mills into the SAG mill. What I want to point out here is the total different applications between the two designs. On the preferential mill side, we require a scrubbing action, and that is to process pebbles and or clay material. But we also need a bit of milling, and that is to break the shells to free ferrosilicon from the shells that are trapped inside the shells. On the SAG mill application side, you can see here very large particles, let's call them rocks. They vary in size between 350 to 450 millimeters long. So huge rocks, and for this type of application, you need this impact grinding to break the larger, harder particles. So let's discuss the mill zone definitions. The rotational energy of the mill is transferred into the mill charge via your liner design, and that pulls the mill content into a kidney shape. The top of the kidney shape is defined as the shoulder of the charge. We've got the eye definition here in the center, more or less. This is a stagnant area where material below this level is moving upwards and material below the eye is moving downwards, resulting in impact grinding. Then a very important area inside a mill is the rising shear zone. More or less in this region of the mill, here we see the most attrition grinding taking place. Then cascading zone, where we see material in free flight, not a lot of grinding taking place. We have the cataracting zone, definitely no scrubbing in this SAG mill, but I specified scrubbing here because we do see a bit of scrubbing action in this preferential mill, but also a small amount of attrition grinding taking place. And then lastly, your toe or impact area inside your mill. So we had a look at the different grinding mechanisms and the zones inside a mill, but how do we quantify which part of the mill is performing how much grinding? One method to evaluate this or to quantify the amount of grinding that's taking place in your mill is to look at the energy distribution inside the mill. So it is defined as the rate of work in the specific zones inside the mill, and it is a function of the collision normal energy and the rate of work. That rate of work is defined as the number of collisions per particle per second. So in this cascading zone, we see very close to zero work being done, material in free flight, so not a lot of interaction there. In the cataracting zone, we see a small amount of grinding being performed. It's a low pressure zone and a low rate zone. The impact zone, this is where we see the maximum impact work, but again, a relatively low rate. And then in your rising shear area, we see the maximum grinding work being done inside the mill. It's a high pressure zone, it's a high rate. If you think about this, this whole charge level is acting on this position or on this location, and the particles have nowhere to go. So an extremely efficient portion of the mill. If we plot the normal impact energy against the number of collisions per particle per second, we get this type of distribution. This is more or less standard for the complete mill, where we see higher impacts at a lower rate and lower impacts at a higher rate. But if I compare the impact zone with this rising shear zone, there's an order of magnitude difference between the number of collisions per particle per second. So this indicates to you how important it is to optimize your grinding mechanism. We need this impact zone to break larger, harder material, but it will happen at a very reduced rate compared to this rising shear zone. What drives milling? Based on the past few slides, we can also ask the question, what makes a mill special? And it is the high interaction rate between the particles and the ore, between different ore particles, as well as the interaction between the grinding media and the ore. We need sufficient energy to break particles. We will see in this case study, excess energy is wasted and low energy is inefficient. As explained already, if you depend on impact grinding and your liner design doesn't provide that impact grinding, it will be inefficient grinding taking place in your mill. Also based on the last few slides, the majority of grinding work is done in the rising shear zone inside the mill. There are many interactions. It's a high pressure zone because the whole charge level acts on that area inside the mill, and the particles are trapped. So they've got nowhere to go. Extremely efficient grinding taking place in that rising shear zone. Then I've added 2 slides on the software that we use during the liner design process. We basically use Multotec as a single particle 2-dimensional simulation tool. We also use the discrete element method that focuses more on the 3D simulation of particles, the movement of particles, and we will look at that just now. And we use the finite element method, and that is to verify the structural integrity of the liner design. So let's have a look at Multotec. It gives you a single particle projection based on the geometric properties of the mill, as well as the basic geometric properties of the liner. It will also calculate the position of the toe based on the volumetric charge level. Moving on to the discrete element method. So the discrete element method, here we can simulate different particle sizes. We can look at the interaction between the particles and the liners. And we can also simulate the wear of the liners. That is a big advantage when using the discrete element method, because you can perform comparative studies to verify the wear life of different liner designs. In this specific simulation, we have superimposed a mil-trash trajectory on top of the discrete element method. And in most cases, we see very good correlation between the discrete element method and mil-trash. Let's look at the liner design parameters. So we have a set of inputs that in most cases are fixed. We cannot really change them, with one exception, and that is the mil speed. If a VSD is fitted, we can vary the mil speed through the liner life, as well as a function of the liner design. On the mil design side, it is the geometric properties of the mil. The diameter of the mil, the length, the head angle, the trunnion diameter, and also the type of mil. On the mil operating parameter side, we take into account the feed particle size distribution, the mil speed or the percentage of critical speed that the mil is being operated at, the ore characteristics, the total volumetric filling of the mil, as well as the volumetric filling of the grinding media inside the mil, and lastly, the liner changeout plan. So during the design process of the liners, and for this case study, let's focus on the shell liners, we look at the wear life, the trajectory that is directly influencing the grind inside the mil, the effective volume of the mil, the throughput, as well as the absorbed power. So the throughput and absorbed power is directly influenced by the trajectory and the mil effective volume. And we will see that also in case study 2. And lastly, very important to also verify the structural integrity of the liner to ensure that it protects the very expensive mil shell throughout. If we drill one level down into a bit more detail on the shell lining side, this cross section here shows a section of the mil shell, shell plates, as well as lifter bars. It also shows the forged T-bolts keeping the lifter bars attached to the shell. So during the design process, we can vary the lifter bar release angle, which is basically this angle here. If we make this angle less aggressive, it means if we increase this angle, we will reduce the amount of impact grinding taking place in the mill. If we make it more aggressive, that means reducing this angle, we will increase the amount of impact grinding, and we can even then overthrow the material that will result in direct ball on liner impact. The height to angle of the lifter bar, that is the distance between the top of shell plate, the start of the release angle. The height to angle influences your wear profile in this area of the lifter bar, and it also influences the trajectory of smaller material inside the mill. Your lifter bar height back, your lifter bar height and shell plate width, all those variables influences your shell plate width to lifter bar height ratio. And that is of significance because that will determine if your shell plate will wear out before the lifter bar, and it will also give you a good indication if there will be some blocking of material between adjacent lifter bars. And then lastly, your shell plate thickness. This will significantly influence your total mill volume as well as your wear life of your liner. Moving on to the case study itself, let's look at the mill operating parameters for this case study. So the grinding circuit, it is a crusher in series with a SAG mill, ball mill, in closed circuit with cyclones. And the focus of this case study is on this ball mill. The ball mill has an overflow discharge, also important to note. Grinding media is correctly sized at 50 mm diameter high chrome balls. It's being operated at a fixed speed of 75% of critical speed. And then the feed size of this ball mill. Extremely small feed size, top size here of 1.4 millimeters. And we will see later on why this is so important. So remember, fine feed size plus an overflow discharge. If we look at the trajectory of the liners in the new condition, we designed this with a small amount of impact grinding taking place on the toe region. We also take into account that there will be some attrition and compression grinding in this rising shear zone. If we take a look at the liners in the midlife condition, we see a total different picture from a trajectory point of view. Firstly, no significant impact grinding in this area of the mill. We still see the attrition and compression grinding doing most of the work, and a small benefit of less material in free flight is that we have increased the cross-section of the charge in this area of the mill. This will then also benefit the amount of attrition and compression grinding because you've got more material acting in this area of the mill. Then this slide shows the trajectory towards the end of liner life. Again, we can see there's no significant impact grinding taking place. Still the attrition and compression grinding. What is important to note that there's almost zero zero impact taking place. This picture here shows the worn profile of the set of liners. And in most cases, when you achieve this wear profile together with this trajectory, it's time to change your liner. For this specific case, let's look at the power draw throughout the life of this set of liners. And it's clear from the SCADA data of the mill, there's a slight reduction of motor input power throughout the life of the liner. And immediately you would say, but maybe there was a reduction in throughput or there was an influence on the grind. This was without negatively influence the throughput or the grind inside the mill. There was even a small increase in throughput throughout liner life. So we can conclude that attrition grinding is doing most of the work in this mill, and then excess energy is initially wasted. The impact grinding is not doing a lot of work in this mill application. We need to take into account, this is an extreme case. In most cases, impact grinding is extremely important, but this case study shows us choosing the correct grinding mechanism for your mill is a priority, and you must sort that out during the first few supplies of your liners. So you have sorted out, or you have optimized your grinding mechanism in the mill. You have achieved a steady state condition in your grinding circuit. Now is the time to optimize your liner. So optimization always seeks a balance, and I've included two examples. The first example, increase the mill volume and or the effective grinding length. The positives is a higher throughput, also higher absorbed power plus an improved grind. On the negative side, if you increase this without considering the rest of the liner design, lower discharge capacity and reduced liner wear life. Second example, if we increase the discharge capacity significantly, we expect a higher throughput and we also expect a higher absorbed power with an improved grind. On the negative side, possible shell liner damage towards the discharge end of the mill, and that is because we can pull the mill empty with this increased discharge capacity. Also, we can reduce the mill volume and the effective grinding length, and that will basically counter the higher throughput and the higher absorbed power. So we can conclude a mill liner design seeks the optimum balance between grind, liner life cost and throughput. As part of this case study, I want to also look at how to calculate or predict the input motor power for your mill. There are various different formulas available and various different methods available to estimate or predict the input motor power. I like the Morel predicted power model. It's an online power calculator. And the reason I like this model is because it gives you the limits, the minimum and maximum limits of the model. It also clearly explains on the website what are the limitations as well as how this model is derived based on actual measurements in the field. Then it also gives you a plot against the measured power draw, against the calculated power draw, and it is very accurate. Let's look at the input variables required to estimate the motor input power. Mill diameter, you can see here on the right hand side the limits of this model. I'm not going to go through each limit. The effective grinding length of your mill, that will influence the input power. Whether it's a discharge, overflow discharge or a grade discharge, that will also influence the absorbed power. Fraction of critical speed, your liner thickness and your geometry of your feed and discharge. On the mill content side, and here I can say that these variables influence the absorbed power to a lesser extent. So important to get these exactly right. And then this doesn't play a very big role on the absorbed power. Your ore SG, liquid SG, fraction of ball filling. Just a correction here, your fraction of ball filling does play a significant amount, a significant role in the input power, but you will know this. You've got good control over this and you can specify this accurately. Your total filling, if it's a SAG mill, and then percentage solids by weight of the discharge slurry. If we look at a typical example using this mill input power, the motor input power model, I've done a sensitivity study here, varying the percentage ball filling and then calculating the corresponding input power. You will see there is a significant impact when you vary the percentage ball filling. And interesting to note, the model does account for an overflow discharge and for a grade discharge system. So why do we see this deviation or this difference between the grade discharge at the top and the overflow at the bottom? There's a tendency for an overflow discharge to absorb less power. And we can say it's always advantageous, but that will not be 100% correct. So if you take into account that an overflow system will form a slurry pool in the mill, it can have a negative impact or influence on your impact grinding and your final grind inside the mill. So let's move over to the actual case study. And this case study is all about optimizing your liner life as a function of the mill effective volume and the mill absorbed power. The mill operating parameters, it's a 6.1 meter SAG mill with a grade discharge, 125 millimeter diameter steel grinding media. It's being operated at 75% of its critical speed with a conventional geared drive. What did we do and what did we achieve with this specific case study? So over a few supplies, we have optimized the liner profile and the liner design based on the actual wear profile. This is based on condition monitoring being performed in the mill. We have aligned the liner life with the plant maintenance plan. Initially, the liners exceeded the required maintenance intervals, and we've aligned that with a result in a 20% reduction in liner thickness. So the end result for the customer, a 1.4% increase in mill volume, a 1.7% increase in motor input power, and this will correspond to the increase in throughput in the specific mill. And then also of significant importance, a reduction of 15% of the liner cost. So guys, let's discuss a design comparison between a radial and spiral discharge design. So I want to kick off immediately with the introduction to mill discharge systems. On the left-hand side, we can see an overflow discharge system. This is the main types of discharge designs, an overflow on the left-hand side and a grade discharge on the right-hand side. From Multotec's point of view, we see the grade discharge system as a critical area of improvement in the mill liner design. Let's look at the characteristics of both designs. On the overflow discharge system, it's appropriate for ball mills and rod mills, mostly secondary and regrind ball mills. The material level is controlled by the discharge trunnion diameter. So it's basically controlled by the mill geometric properties. The product particle size distribution in an overflow mill is less steep compared to a grade discharge. We expect a finer grind in an overflow system compared to a grade discharge. And then, as pointed out with the power calculation, there's a slight reduction in power draw for an overflow system. Not always an advantage, as I explained. The slurry pool, although it offsets the torque requirements in the mill, and that will reduce the power draw, it can also reduce your impact grinding happening in that overflow mill with a negative effect on throughput as well as grind. The typical characteristics of a grade discharge system. So it is necessary for large diameter mills, and that is to maintain an acceptable charge level. It is appropriate for the larger sag and ag mills and also larger primary ball mills. We see an increase in throughput compared to an overflow discharge design. So it is definitely more efficient. It works the same as a pump, so definitely more efficient. It does not allow large grinding media to go out of the mill to pass through the mill. This is also a big advantage. Then two negatives on a grade discharge design. The mill can be pumped or can be pulled empty towards the discharge end of the mill. So I've explained that this grade discharge is very similar to a pump. So if you don't feed enough material into the mill, you will pull your mill empty towards the discharge end with direct ball on liner impact. Flow inefficiencies. We will look at this. This is an area of improvement and development in most discharge systems. Flow back and even carry over in your pulp system, and this is due to flow efficiencies, problems with the geometric design of the pulp lifter. Lastly, not a disadvantage, but just a characteristic, the percentage grade open area needs to be sized for the application and the type of mill. During case study 1, we discussed the input variables in the mill liner design, so we're not going through this again, but let's take a look at the grade discharge design variables. First, liner life. How can we influence liner life on the discharge side of the mill in a grade discharge system? Material of construction, liner thickness, and then also very important, lifter bar height and lifter bar width. The lifter bar will protect the grade plate and the lining system on the discharge head. The open area, also a very important variable in the design. Then two geometric design variables, the pulp chamber length or depth, as well as the pulp chamber cross-sectional discharge area. In the next slide, we will look at the pulp chamber length, and we will also look at the flow inefficiencies going on inside a grade discharge system. Mill effective grinding length, this is influenced by your discharge design. If you oversize your discharge design, you can negatively influence your effective grinding length inside the mill. And then your discharge efficiency, this is basically a function of your mill open area and your geometric properties of the design. So how do we size the pulp chamber depth or the pulp chamber length? One way of doing it is to look at the superficial discharge velocity. So the superficial discharge velocity, or SDV, is the volumetric flow rate per unit open area in your grate. So when you look at the volumetric flow rate measured in cubic meters per hour over square meters, the unit of measure for SDV is meter per hour. And that gives you a very good indication of your slurry discharge capacity of your grate discharge system. This formula shows how to calculate SDV, and it is obtained from a published paper, Slurry Pooling and Transport Issues in SAG Mills by Malcolm Powell and Walter Valerie. So your SDV is a function of the fraction grinding media in your mill. This is the only method that I'm aware of that takes into account this very important variable, the fraction grinding media in your mill. We then see the pulp lifter length, which is basically that I mentioned there. And this is what we want to achieve or obtain from this formula, is to calculate the pulp lifter geometry or the pulp lifter length. The mill circumference, the input variable, the effective grinding length, and then the radial position of the apertures. On this point, this is the weighted average position of the apertures. So it's not just the average position, but the weighted average position. We then aim to achieve a SDV value of between 150 to 200 meters per hour, and we solve for the pulp lifter length. This will ensure optimum discharge capacity. And the question is this enough? The answer is no, it's not enough. We need to look at the flow inefficiencies inside the grate discharge system as well. Flow inefficiencies that can cause slurry pooling in a SAG mill, in a big SAG mill, slurry pooling that can reduce your absorb power and throughput by up to 10%. And this is due to reduced throughput of your discharge system. The solution to this is to investigate better geometric layouts, as well as to look at spiral pulp lifters that we will look at now. The flow through the mill, so there's the transport of slurry and ore particles. It passes through your grate. The pulp lifters then lift the material up, and the aim here is to direct the material towards the center of the mill so that it can discharge toward the outside. Inefficiency number one, flow back. This is when material flows back through the grates back into the mill. It is a major concern for grate discharge systems. Inefficiency number two, carryover. Carryover is when your pulp chamber content flows to adjacent pulp chambers. So it doesn't exit the mill, basically gets transferred to the adjacent pulp chamber, and then eventually it ends up going another rotation in the mill. And then lastly, what we want to achieve, we want to discharge the material towards the outside of the mill. Moving on to the actual design comparison between the radial and spiral pulp discharge system, what did we want to achieve in this study? First of all, we wanted to increase the throughput for future expansion for this customer, and specifically to eliminate flowback and carryover in the discharge design. The customer also requested to double the wear life of the discharge system. So this was a very big challenge. If we look at the mill variables or the mill parameters, 6.4 diameter mill, 4 meters long SAG mill. In the study, we've used the discrete element method extensively, and we did a comparative study between the radial and the spiral design. In the DEM simulation, we've used a partial shell model, and we've modeled the complete discharge system. Charge level 25%. We've accounted for a PSD, particle size distribution, inside the mill by simulating different grinding media sizes. And then important to note, we didn't simulate the actual flow of material from the mill into the pulp chambers. We calculated the amount of material that needs to go into the pulp chamber. Like I said, the aim of this study is to compare the radial and spiral design to see if we can design a spiral design that is more efficient compared to the radial design. So let's look into this. We calculate the amount of material going into a pulp chamber per rotation to be 13.7 kilograms of material. This is based on the increased aimed throughput already. So here we've got 200 tons per hour. If we convert that to tons per minute, we get 3.3 tons per minute. And the resultant amount of material entering the pulp chamber is then 11.4 kilograms. On top of this, we've added a 1.2 or a 20% contingency factor, and that is to account for possible flowback and carryover in this design. This slide shows the radial design. It's already the upgraded design where we've increased the wear life from 26 to 52 weeks. We've increased the lifter bar height significantly, as well as the width of the lifter bar. The grade plate itself is the Multotec Multomed design, which is basically a combination of rubber and Hardox 500, also to counter the wear. Moving towards the inside, we have an integrated liner where we have integrated the lifters into the head plate. And this is based on the heavy-duty Multomed design, where we used chrome moly inserts to counter the high wear areas. On the inside, we have a protection liner. And then outside the Multotec scope, we've got the central discharger in this position. And I also want to point out this scroll return or this return feed pipe. The function of this return feed pipe is to feed scats back into the mill. So Mohini has indicated that the pebble crusher connected with a magnetic separator, that is the most efficient way to get rid of scats, and I totally agree with that. But this system, the return feed pipe system where you feed scats back into the sack mill, it either works for you or it doesn't. In this specific application, it works. Moving over to the spiral discharge design. So as you can see here, it is based on the radial design, but with spiral geometry. The grade plate is a Multomed design, rubber matrix. Correction, it's a rubber submatrix with a Hardox 500 matrix to counter the high wear areas. If we take a look at the steel lifter bar design, the spiral geometry is clearly visible. So you would ask, why is the spiral not more aggressive? Can't we increase the aggressiveness of the spiral to even increase the throughput even more? The answer there is no. The spiral geometry is a function of your drilling pattern, as well as the open area required inside the mill. So by modifying a discharge design from radial to spiral, you inherently increase the length of your lifter bars. If you take this into account, a straight line will be shorter compared to a curved line. So there's more lifter bar material in the spiral design on the discharge head compared to a radial design. It is a small disadvantage, but with a proper design, you can optimize your open area with the spiral geometry. Then also, as discussed in the radial design, this is the head plate design. It is aimed for larger sack mills. It's a heavy-duty Multomed design with chrome moly castings, and it combines two lifter bars into an integrated head plate. Protection liner, and then I would like to focus on the pulp lifters. We've got two different pulp lifter designs, pulp lifter A, pulp lifter B. Pulp lifter A, the dividing web stops close to the central discharger, where in pulp lifter B, the pulp lifter web are shortened, and that is to increase the cross-sectional discharge area in this area of the of the discharge system. Let's look at the results obtained from the discrete element method study. First of all, this is the mill in the 6 o'clock position, and it indicates the ore particles in the pulp chambers. The significance here is that when you convert from a radial to a spiral design, you need to consider that if the spiral design is very aggressive, if you've got very aggressive geometry here, you can lock material inside the pulp chamber. So we have optimized this design to prevent locking of material in this portion of the mill. This slide indicates the position of the first discharge chamber. If I say first, we filled 12 discharge chambers with ore with a 13.7 kilogram of material, and it shows a comparative plot between the spiral discharge and the radial discharge. Clear from this plot that the material in the pulp chamber is already very close to the central discharger, so it indicates that it discharges quicker and more efficient compared to the radial design. You can see here in the radial design, there's still a lot of material on its way towards the central discharger. This specific view shows the last pulp chamber. If I say last, this is the last pulp chamber that was filled with material. So it's the last pulp chamber in the 12 o'clock position. And again, very clear that the spiral discharge system discharges quicker towards your central discharger compared to a radial design. We will discuss carryback and flow over during the next slide, the next two slides. This slide here gives you an excellent view of the shortened pulp lifter webs, and that is to increase the cross-sectional area in this area of the discharge design. So you can see we've incorporated this improvement in both the radial design and the spiral design, so no significant difference between the radial and spiral design with regards to the cross-sectional area towards the center of the discharge system. Guys, then I would like to play a DEM simulation. This one indicates the spiral design, and it's showing the kidney shape inside the mill. As soon as the ore reaches the 6 o'clock position, we hide the kidney shape. I just want to play this again. As soon as the ore reaches the 6 o'clock position, we hide the kidney shape. You'll see that it enters the 6 o'clock position, and we can clearly see the discharge and the discharge rate in the spiral design. Let's compare that to the radial design. Again, you will see as the ore comes through the 6 o'clock position, we will hide the mill content, and you will be able to see the discharge towards the center. Now let's freeze this video or this simulation when that last portion reaches the 12 o'clock position. So guys, as you can see, a direct comparison between the spiral and the radial design. For the spiral, when the material is in the 11 o'clock position, it's already in contact with your central discharger. There's a very low probability of material flowing to adjacent pulp lifters, so it is more efficient compared to a radial system. With the radial system, I can actually move it on slightly. But you can see with the pulp in the 12 o'clock position, there's still a lot of material in the adjacent pulp lifters. This can now either flow back into the mill, or it can flow into adjacent pulp chambers and go around again, causing inefficiencies in your discharge design. So what do we take away from this? In case study 1, we said it's all about the grind. And Ernst will also confirm this in his presentation. The mill is the only machine in your milling circuit that is doing the grinding work. So getting the correct grinding mechanism must be a priority. We also seen that every mill application is unique and a custom-made liner design is required to maximize the mill efficiency. And without a proper mill liner design, an increase in absorbed power would not necessarily result in an increase in throughput. From case study 2, this was all about the throughput. So you have achieved your grind, you've achieved your steady state condition in your milling circuit. Now is the time to optimize your liner design. And we said a mill liner design seeks the optimum balance between liner life, cost, and throughput. It's not all about life and cost. You need to consider throughput as well. Lastly, the design comparison between the radial and the spiral discharge system. From Multotec's point of view, this is a critical area of improvement inside your mill. We need to optimize that great discharge system. The spiral design compared to a radial design improve the discharge efficiency of your mill significantly. It can also increase the throughput if correctly designed. And what we've also seen from the DEM simulation results, the spiral design have a lower probability of carryover and flow back into the mill. So guys, what I want you to take home, perform small incremental changes to the liner design to optimize the design, and at the end of the day, you will see the benefit. Thank you. Thanks for your time.